Hello everyone, and welcome to my video on simple gas laws. Hopefully this will help you if you're studying for your Unit 7 test to know how to do these problems. The simple gas laws help us answer questions like what we did during the can crushing lab. So during the can crushing lab, we had a Coke can, and we put some water in there, we heated it up, and it started steaming, and it got all steaming. There was a gas in there, and then we dunked it in some ice water, and the can crushed. So we decreased temperature, and our can crushed, or our volume also decreased. So understanding our simple gas laws helps us to understand this kind of situation we see during lab. Okay, things we need to know for simple gas laws: we need to know V is volume, and volume is usually found in liters. T is temperature, and that's usually found in Kelvin or in degrees Celsius. If you have it in Celsius, you have to convert it to Kelvin before you can put it in the equation. So you would add 273 to Celsius, and then you would have Kelvin. If it's already in Kelvin, just leave it in Kelvin. Pressure is either going to be in ATM, millimeters mercury, or kPa, and you can use all three of those. During this video, I'm going to try and use red for my initial conditions and blue for my final conditions. Okay, our first law is Charles' law. So that's volume and temperature are directly proportional. So if temperature increases, then volume will increase. If temperature decreases, then volume will decrease. And this is what we saw during the can crushing lab. We decreased our temperature by putting it in ice water, so then volume decreased, or can crushed. Our other law is Boyle's law. That's pressure and volume are inversely proportional. So if volume increases, pressure decreases. If volume decreases, then pressure increases. Gay-Lussac's law is pressure and temperature, and they are directly proportional. So temperature increases, pressure increases. Temperature decreases, then pressure decreases. This can be kind of difficult for us to visualize, so I drew this little picture. So hopefully this will help you to understand what's going on. I have a certain amount of gas. I drew 7 gas particles because I didn't want to draw that many in this container. So let's say that this is my 7 gas particles, this is my container, and I'm going to increase the volume of my container, or increase the space that my particles will take up over here. So if I've increased my volume and made my box bigger, I still have the same number of particles. They're just more spread out. There's just more space. My pressure, or my collisions between my particles, is going to be lower. They're going to run into each other less. If I decrease my volume or my space, put it in a smaller container, then I'm going to have more collisions between particles, or a higher pressure. The same thing works with temperature. So our speed of particles is our temperature. So if you increase your temperature, your particles are going to be moving faster and faster. If our particles start moving faster in this box, then they're going to run into each other more, and we're going to have a higher pressure. If they're running into each other more and has a higher pressure, and our box has the ability to expand, then it will, and it will increase volume. Temperature decreases, that means our particles are going to start moving really slow, and they're going to be colliding with each other less, and we're going to decrease our pressure. And if our container has the ability to compress, then it will. Okay, hopefully that helps you understand the relationship between these 3 variables. These are the laws that you're going to have to do on the test. We've got Charles' law, Boyle's law, and Gay-Lussac's law. These are the ones we're going to look at when we are doing our word problems and plugging in our numbers. So let's do one together. We've got 25 liters of gas. It's cooled. Its volume decreases to 12 liters. The initial temperature is 55 degrees Celsius. What was the final temperature? Remember to use Kelvin. So I'm going to use red for my initial conditions. So I see 25 liters of gas cooled, then to 12 liters. So liters, remember, is volume. So I'm going to label this as V1. And then it decreases to 12 liters. So I'm going to label 12 as V2. Initial temperature is 55, so I'm going to label that as T1. And then what is the final temperature? T2, we don't know, so that's the one that we're going to solve for. Let's plug it into our equation. We have V and we have T, so we should go over to our equations and find the one that has V and T, which is Charles. So that's the one that we're going to use. If you try to use one of these, you won't have anything to put in the spot for P. Okay, so 25 was V1. T1 was 55 degrees Celsius. But remember, you can't put Celsius into the equation. So I need to add 273. So 55 plus 273 is 328. And that's what I can plug in my equation. Okay, V2 is 12. And T2 is the one we don't know. And that's the one we're going to solve for. So our goal when we're solving for an unknown variable is to try and get that variable all by itself on one side of the equation. When you have something in the denominator, the first thing you need to do is get it out of the denominator so that you can solve for it. The best way to do that is to do the cross multiply or butterfly situation that hopefully you've learned in math class. So I take these two numbers, multiply them, and then set it equal to these two numbers multiplied. So I'm going to say T2 times 25 equals 328 times 12. Okay, I'm going to simplify this just to make it easier on myself. So T2 times 25 is going to stay, and then I'm going to do 328 times 12 in my calculator, and I get 3,936. Okay, I want to get T2 all by itself. So right now, T2 is being multiplied by 25. If I do the opposite, it will cancel out. So I could divide by 25, and 25 will cancel out. Now T2 is all by itself. If I do something to one side of the equation, I have to do the same thing to the other side. So I'm going to divide this by 25 as well. And I end up with 157.44. We're going to round everything to 2 decimal places. On the test, it's multiple choice, so just choose the closest one. And this is temperature. If we put Kelvin temperature into the equation like we're supposed to, then we will get Kelvin temperature out of the equation. So Kelvin is going to be our unit. If you're asked for Celsius, you could subtract 273, and that would give you Celsius. But we're not going to do that because it didn't ask us to. Okay, so that's Charles' law. Hopefully that's helpful. Our next example we're going to do says a gas at constant volume has a pressure of 755 millimeters mercury at a temperature of 223 K. What is the pressure at 115 K? So I'm going to look at what I have. I see 755 millimeters mercury. That's my starting pressure. So I'm going to call this P1. Because remember, millimeters mercury, ATM, and KPa, those are all pressure units. And then a temperature of 223 K. So I'm going to call this T1. What is the pressure at 115 K? So it gives me a second temperature. This is going to be T2, and then it's asking me for pressure. So I'm going to plug these numbers into the equation that works. I've got pressure and I've got temperature. My equation over here that has pressure and temperature is Gay-Lussac's. So that's what I'm going to plug it into. So I'm going to take P1, which is 755, over T1, which is 223 K, and I don't need to add anything because it's already in Kelvin. I don't need to change it. And then P2 I don't know, and T2 is 115. If you like the butterfly cross multiply situation, you can do that here, but you don't have to since you're not solving for something in the denominator. Since you already have your variable in the numerator, you can just get rid of 115 and then P2 will be all by itself. So I'm going to do that. I'm going to do times 115. It's going to cancel out, and then P2 is going to be all by itself on this side of the equation. And then I'm going to do, if I do it to one side of the equation, I need to do it to the other side. So I need to multiply this side also by 115. And then this in my calculator is going to be the answer to my question. So I'm going to say 115 times 755 divided by 223. And I end up with 389.35. Once again, I took 115 times 755 divided by 223. And I got this answer for P2. So since it's pressure, my pressure unit is going to be the same pressure unit I put into the equation, which was millimeters mercury. And that's the answer. Yay! Okay, we just have one more left to do. 2 liters of gas is at a pressure of 3.5 atm. Under what pressure does it decrease to 1.5 liters? So my initial, I see 2 liters right here. Liters is volume, so I'm going to call that V1. And it's at a pressure of 3.5 atm. So that is pressure, ATM is pressure, so I'm going to call this P1. And then it asks me under what pressure does it decrease to 1.5 liters. So 1.5 liters is going to be V2, because liters is volume, and that means that I'm solving for P2. I don't know what P2 is. I've got pressure and I've got volume, so I need to go back to my equation and find the one that has pressure and volume. That's going to be Boyle's law. So this is the law that I'm going to be using, that I'm going to plug my numbers into. So it looks different than the ones we just did. It doesn't have a fraction. It's just multiplication. Okay, P1 is 3.5. V1 is 2. P2 we don't know, so I'm going to put P2 as my placeholder variable. And then V2 is 1.5. Okay, and I think this is the easiest one, because then all you need to do is get rid of 1.5 over here so that P2 can be by itself. So whatever you need to do to get that variable by itself, that's what you should do. So I'm going to divide by 1.5, and that means it's going to cancel out. P2 is by itself. And if I do something to one side of the equation, I have to do it to the other side. And then this is what I'm going to type in my calculator. I'm going to say 3.5 times 2 divided by 1.5. And I end with 4.67. And once again, this is pressure. So whatever my pressure unit was that I started with in my equation is going to be the unit that I use here, which was ATM. We didn't do one with KPA, but that's okay. It works the same way. I hope that this was a helpful overview of the simple gas laws. Please, please, please email me with questions. I would love to answer them. Hopefully this helps. Okay, bye.